Acid-base homework. The first set of instructions here, this isn't actually a question. I would like you to make sure that you understand how to calculate the pH in a strong acid, strong base titration, but I want you to see this example that's linked here in order to see how that's done. So practice that one on your own. Now we're going to answer a series of questions with these conditions. So if we have a titration of 40 milliliters of nitrous acid, and we're going to titrate that with potassium hydroxide, what we're showing is a weak acid, strong base titration. So with that titration, we have several different situations. So this is weak acid, strong base. So at first, we're asked to calculate the pH of the acid before any base is added. So we're going to need the Ka of this acid. Well, to find that Ka, scroll all the way down to the bottom, and you'll see that the dissociation constants, or the Kas, are linked in for you. So you just have to find the right acid. So here I'm looking for nitrous, starts with an N. So my Ka is 5.6 times 10 to the negative 4. So the first pH is no base. And the Ka is 5.6 times 10 to the negative 4. Now we just have a straight weak acid solution in this case. So I'm just going to have my generic weak acid dissociation here, breaking into hydrogen and conjugate base, my appropriate ions. So because we just have a weak base, we don't really have to worry about the moles. We can just use molarity. So at equilibrium then, we're going to change by some amount, x. It's not quite an x. So at equilibrium, my Ka will be equal to the product of my products, x times x, divided by my reactants. Now because the Ka is fairly close to my original concentration, I'm going to simplify. I'm actually going to work this both ways, and I'm going to show you that in this case, we're very close to the 5% rule, and we actually end up with a pH that's within the margin of error. So I am going to simplify here, and I end up finding that x is equal to 7.48 times 10 to the negative 3. I put that into my calculator because that is the molarity, so that is put that in my calculator, take the log of that, the negative log to be precise, and the pH is then 2.13. Now when I work this out and solve it with the quadratic formula, so no simplification, I end up with a pH of 2.14, and that's within our margin of error, and the system will take both of those answers. So 2.13 is the pH of this solution before we add any base at all. Then we have the second scenario. In the second scenario then, we have added some base, and in this problem I'm given, it's 11.73 milliliters of my KOH. So what's the new pH? Well, now I need to calculate my moles. So on either side of the equivalence point or anything other than 0, we need to look at the moles that we have. So we start with 0.00400 moles of acid. And I got that by taking my volume, in liters, and multiplying it by the concentration. So that's moles per liter. Liters cancel out, multiply those things together. Now I also need the moles of base, and I get the moles of base by taking the volume of my base in liters, 1173, that's capital L liters for my base, and multiplying it by the molarity of the base, moles, liters. Liters cancel out, I'm left with moles, and I get that I have, so this is my acid, 0.0023446 moles of base. Now I left all of my digits and performed this calculation, even though 001654, even though this digit isn't relevant to significant digits, I want to avoid as much rounding error as possible. So when I neutralize my acid with my strong base, I'm left with this amount of acid left, and this is moles of acid. Now I have made this number of moles, 0.002346 moles of my conjugate base, because that's how much acid has been neutralized by the base in order to force it over to that conjugate base. So now I can use the Henderson-Hasselbalch equation. Remember that the Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of the ratio of the conjugate base over the weak acid. Now we could calculate molarity, or we could just leave these in moles. Find the pKa. In order to find the pKa, you put the Ka, you take the log of the Ka, drop the negative sign. So I get a pKa here of 3.25. And then in my calculator, I'm just going to use the moles. So 0.002346 and 0.001654. Calculate all that together, and I get a pH value of 3.40 after 11.73 milliliters of KOH have been added to my weak acid solution. So now what's going to happen then? What is the pH after 20 milliliters of this solution has been added? So 3, I need 20 milliliters of KOH. This was a pH of 3.40, and this was a pH of 2.13. So now I have this 20 milliliters of base. So again, with my moles, I start with 0.004000 moles of acid, but now I've added 0.004000 moles of base. So the base that was added has neutralized all of the acid. Now that pushes this amount of base into that amount of conjugate base. So what we've done is we've forced the acid to dissociate. So now we have that amount of our conjugate base, and it's going to react with water. So now the pH is going to be dependent on this equilibrium. So we have this molarity in order to do this calculation. So I need the total volume. Well, we started with 40 milliliters of acid, and we have 20 milliliters of base. So we have a total of 60 milliliters. Converted to liters looks like this. So the capital M molarity of this solution, so this is what we're working with now, is 0.0667, and the 6 actually repeats, and I leave that in my calculator. And we have no weak acid left because we've converted it all to conjugate base, and we have no hydroxide yet. So this was my initial. We're going to change it by some amount X. And then at equilibrium then, we have these values. Now this is not a Ka, this is a Kb. So recall that a Kb can be calculated from Kw and Ka. When I take 1 times 10 to the negative 14 and divide it by the Ka, 5.6 times 10 to the negative 4, I get a Kb value is equal to 1.7857, and then there's more digits I'm leaving it in my calculator, times 10 to the negative 11. So at equilibrium then I can calculate for these x's. So again, 1.7857 and other stuff times 10 to the negative 11, and that's going to be equal to the concentration of my products at equilibrium, which is going to be x squared since I'm multiplying them together, divided by the concentration of the reactant. It's safe to say that I can simplify this. So when I multiply both sides by 0.0667 and then take the square root, I find that the x value is 1.09 times 10 to the negative 6 capital M molar. Now recall that this x value is the concentration of the hydroxide. So because it's in my calculator, I can take the POH here, and the POH is 5. I think that's a 9. I can hardly read my writing. It might be a 4, but I believe it's a 9.6. And then the pH is related to that. So the pH is going to be 14 minus the POH So the pH ends up being 8.04. So I'm going to go up here and I'm going to record that the pH is 8.04, and that is at the equivalence point. Recall that the equivalence point is where the moles of acid equal the moles of base. Now, because this is a weak acid and a strong base, that equivalence point is greater than 7. And the reason it's greater than 7 is because all of that conjugate base has been converted, or all of that weak acid has been converted into conjugate base, and it reacts with water in order to form the hydroxide ion. So in the fourth scenario then, we have 27.08 milliliters of KOH added, also asked to find the pH. So now we have exceeded the equivalence point. So I'm going to go back to my moles here. I have 0.004000 moles of my weak acid. And now I have more moles of base than I do acid. So I need to find out what the excess base is. So I take the volume of base in liters and multiply it by the concentration of the base, and I am left with moles of base. So I get 0.06 moles of base. And then I'm going to subtract the acid from that to give me how much excess base I have. And I find that I have 0.001416 moles of base in excess. So now the pH is going to be purely dependent on this base. Because it's a strong base, we just need to find the concentration now. So I need to divide these moles by the total volume. Now the total volume here is 67.08 liters. 67.08 milliliters converted to liters is going to look like this. So the new concentration of my hydroxide then is going to be 0.211, and there are more digits. I'm giving you extra digits intentionally. POH, because it's already in my calculator, it's pretty easy to find. The POH is 1.67, and then it keeps going, but we need the pH. Now the pH is going to be 14 minus the POH, and I get that value to be 12.32. So that's the number I would record in the quiz. So I come back over to my quiz, and I believe they all say to the nearest hundredth of a pH unit, which makes it easier. So the first one was 2.13, the second one was 3.40, and the third one I got 8.04, and the fourth one I got 12.32. Now, like previous quizzes, you need to insert your answer for any credit, and then you're welcome to send me your handwritten work with the appropriate assignment after the fact. Number 5, what's the pH of a solution of 0.18 of our weak acid and this amount of our conjugate base? Now you're given the Ka here, so use the Ka given if at all possible. So I come over here, this is a Henderson-Hasselbalch equation. So pH equals pKa, or a Henderson-Hasselbalch question, plus the log of the ratio of the conjugate base to the weak acid. So now I just plug in my numbers. I was given my Ka value, so I can find that pKa, and it's 4.74. Then I take the log of the ratio. So I put my conjugate base, 0.038. The conjugate base is going to be the salt, divided by the original weak acid. So I find when I plug this into the calculator that I get 4.06 for my pH. So that is what, and it says to the nearest hundredth, so that is what I would report in my question. Number 6, write the ionic equation for dissolution in the solubility product expression for the slightly soluble compound this. Well, it might be easier if you start by copying and pasting that. And then make sure you put some phases in. Now, I don't expect you to know HTML to know what the arrow code is and click the HTML editor. You can just show me a double-sided arrow. So you can do that with your less than and equals and then a greater than, or you can do that with less than, a dash, and a greater than, but show me a double-sided arrow of some sort. Then we're going to have 2 of our silver ions and then 1 of these. Use the text editor in order to superscript the charges and subscript as appropriate. And give me phases. Remember, the phases do matter when we're talking about this. So now we have a KSP that we have to show, and I'm going to show that KSP. Again, you can copy and paste and makes it go faster. All evidence to the contrary. Make sure to superscript where appropriate so that the KSP expression would have this silver ion squared. That is important. So that's all I need for that question. Number 7, we're going to calculate the solubility product for this. Now, this isn't a compound that I've seen before. So what do I do with this? Well, it is not a typo. These are elements on the periodic table, but it's given to you in a form that you may not recognize. And this is grams per milliliter. Now, when we see solubility product, we think of it as capital M molarity, and that's moles per liter. So how do we get grams per milliliter to moles per liter? Well, we convert it. So if I have, and this is just dimensional analysis, there is no equation for this, it's just a straight dimensional analysis. So if I have this and I'm aiming for moles per liter, then I hope it's intuitive at this point in your chemistry journey that you need to find the molar mass. So I go to the periodic table and I look up my barium and my selenium and my oxygen, and I add them together to get the molar mass, and I get 280.3 grams of this compound, SO4, and that is per 1 mole. So I have canceled out the grams. I'm left with moles per milliliter. But I need moles per liter. Well, you can either do this the dimensional analysis way and put your 1,000 milliliters over 1 liter. You could do it that way. There's nothing wrong with that. Or you can convert this into liters just like that. It's the same amount. Either way works, and you will end up with moles per liter. So when I do that calculation, I end up with 4.21 times 10 to the negative 4 capital M molar. Now that is not my answer. That is not the KSP. The KSP is what I'm looking for. What I just calculated was the value of my X. So now I'm going to look at this compound and how would it break up. So I have my barium and I have my selenate. So this is going to break up with barium ions and selenate ions. And because it breaks up like this, each of these would be an X. There is no squared term or anything because my coefficients are each 1. So the KSP is going to be X squared. This is X, so the KSP ends up being 1.77 times 10 to the negative 7. So to enter that here, I would type in the coefficient part here, 1.77 times 10 to the, and then you must put the negative sign and a 7. No spaces there, just the negative sign and the 7. It says to use correct significant figures for this one. Here we have 3 significant figures in our given value. So we'd have 3 significant figures in our answer as well. So assuming that no equilibria other than the dissolution are involved, we're going to calculate the molar solubility from the solubility product for lead bromide. Well, this case, I'm going to need to look up the KSP, and I would do that by finding my value in the file provided at the end of the homework. So I'm looking for lead bromide. So this is organized by element, so that makes it easier. So here's lead bromide. So my KSP is 4.6 times 10 to the negative 6. So that's information I'm going to need. I'm going to write that down over here. And now I need to know how this breaks up. So I have my lead bromide, and we're going to have an equilibrium. And that's going to be lead ions, I'm leaving the phases off just for brevity, and 2 bromide ions. So when this breaks up, we have an X and we have a 2X. Then the KSP is going to be the concentration of my lead times the concentration of my bromide squared because of that coefficient. Now, I don't have my X. That's what I'm looking for, but I do know that this is equal to 4.6 times 10 to the negative 6. So when I work this through, and 2x squared is 4x squared, and I multiply that by x, I get 4x cubed is equal to 4.6 times 10 to the negative 6. Then I divide both sides by 4, I get 1.15 times 10 to the negative 6. Then I take the cubed root. When I take the cubed root, I finally get to my x value, which is 1.15 times 10 to the negative 6th. The cubed root value, which I'm going to put in standard form, 0.1047, and I get all these digits. Now I'm going to go, how do I insert this? The molar solubility, something times 10 to the something. So I would convert this into scientific notation. So 1.05 it looks like. 1.05 times 10 to the negative 2, because I'm going over 2, 1, 2. If you gave me 1.0, just 1.0 times 10 to the negative 2, I would accept that as well. Number 8. What are the equilibrium concentrations of each species in the following buffer? Well, here we're given this amount of stuff. So that's where we're starting. So I have my weak acid, I have water, that's reacting to form my hydronium ion and my conjugate base. So I start with 0.355 moles or molar of my weak acid, and then I also start with some conjugate base because that's what we do when we have a buffer. So I'm going to remove some amount of my weak acid and I'm going to add some amount of hydronium and conjugate base. Now I know that this is the way that my buffer is going to go because I started with no hydronium ion. And because I started with no hydronium ion, I can only add to it. I can't take it away. So at equilibrium, which is what we're concerned about, we have these concentrations for our species. So now we need to find the Ka. The Ka of this is 1.8 times 10 to the negative 5, and that's going to be equal to the concentration of my hydronium ion times the concentration of my conjugate base over the concentration of my weak acid. So I plug in what I know, or what I have, and solve for what I don't know. Now we are on the cusp of not being able to simplify. I'm going to simplify. And then I find that x is equal to 2.84 times 10 to the negative 5. Now that is molarity, which is the concentration of my hydronium ion. So I can add that, or I can insert that right here. And I'm going to put that in standard form. If you want to put that in scientific notation, I'll try to get the system to take it. However, I will grade this manually. And then our effective concentrations of weak acid and conjugate base are the same because this amount is so small relative to these things that you're not going to notice that difference. So those are the answers there. Equilibrium concentrations. Now also be sure that you can explain situations like numbers 1 through 3 at the top of this page. I need you to be able to choose an appropriate indicator and figure out if a precipitate forms. Now I didn't put those in the homework. You need to practice those on your own, but they are on the quiz.